Welcome, everyone. The last session of the day. It's lightning talks after this. Don't forget to come for the lightning talks as well. Hi, I'm Victor, and for the better part of an hour and a bit, we're going to talk about spooky action at a distance. I've a little bit of background. I've always worked on developer tools. I've been building for around 17 years. Advanced installer, then I built some open source tools for bridging the gaps between what's available for Visual Studio users in terms of LLVM and Clang tooling. And recently I moved to the Visual C++ team in Visual Studio at Microsoft. You can find me online in the usual places like Twitter, Mastodon, and so on. So spooky action at a distance. What's that all about? Some of you might know the quote, and it's about entangled particles and the idea that the behavior and interaction of tiny particles are kept linked to each other even when separated by very, very long distances. And this is very relevant to the subject of today's presentation. And maybe an alternative title would have been Revisiting Observers, or subscribe to Observer. And when you usually say observers, of course, people think about design patterns and classical implementations of such paradigms. By the way, I do encourage you to interact. So feel free to ask questions, comment, raise your hand. I'll make sure to repeat the question for the recording. So I will start with right off the bat saying that I kind of hate the term design patterns, not the patterns themselves, but the way they're usually taught or the way people learn about them. And the reason is that it kind of implies that are universally applicable solutions to some common code scenarios. And the mere fact of codifying existing practice into some rules and blindingly following them might be a comfortable path, but it's not always an optimal one. So it's not as easy as following recipes. Sometimes each solution has a unique best associated strategy, and of course it's valuable to know and to identify such strategies, but we have to know how to adapt them and find the optimal one for a particular need. So there is value in having some uniform code structure throughout the project. It requires that we're aware of such idioms, and we need to carefully examine how they fit into our projects or into the workflow that we're trying to implement. Of course, most people think about this book when you talk about design patterns, but I wouldn't recommend people start with this one. I find it too formal and dry. I'd recommend this one. Although it has game in the name, you don't have to be a game dev to use this book or learn from it. I find it much more practical, the examples much more useful and grounded in real needs. So I do recommend this one by Bob Nystrom. And a presentation that is related with design patterns, a fairly recent one by Klaus Eagleberger, is all about facts and misconceptions about design patterns in general, not just the observer that we're going to tackle today. Design patterns have been proven to be useful for over several decades, and knowledge of them is still important in designing robust and modular systems. However, there's a bunch of misconceptions and myths around and misunderstandings about how they should be used, when each one is appropriate, There's a myth around some patterns that should be avoided, and people keep trying to make lists of blessed patterns and so on, and recommending implementations. I think that presentation by Klaus does a good job of separating some of the facts and misconceptions and identifying some common idioms in practice. In terms of inspectable properties of objects, when we come back to the subject of the talk, observer, what can we say we learned from years of object-oriented influence from other languages and frameworks? And can we leverage these borrowed techniques in a heavily value-oriented context? C++, modern C++ tends to lean more on value semantics rather than object networks and references everywhere. And can C++ benefit from special considerations with regards to how we connect these things, the structure and the semantic that the code can deliver? We'll try to discuss these aspects. And we'll visit the observer pattern from theoretical considerations and mostly practice and code. We're going to see a lot of code. But I'm not going to offer a solution, the unique solution, the greatest solution. I'm going to offer some strategies. And each of them will have some drawbacks. And I'm going to try to highlight as best as I can what I find good or bad with each one. So there's, as always, there's trade-offs. So observers are everywhere. If you're familiar with some of these terms on the slide here, like MVC, MVVM, signal slot mechanisms like in Qt, the usual GUI model interactions, loose coupling, but also like, not necessarily tied to GUI frameworks, might be interactions like model to model, where you want to have some level of loose coupling. So these kinds of interactions are everywhere. And let's try to establish a common vocabulary so we don't get confused when we talk about different parts of the system. So I'm going to try to make this as a show with actors and actions. So a subject or an actor doesn't know what type its observers are. So we have actors, actions, their actions, and some observers. And these all are loose coupled components in a system. So the subject, the actor, only knows that it has some observers, and it knows it has a means of notifying them when certain actions occur. And we're going to talk about how we register for those actions. And it's a subscription model, basically. You tune in to a particular radio station. Like you're the observer, and you tune in to find out about certain triggers, certain actions from such actors. So that's what I mean by spooky action at a distance. I mean the way we find out about a remotely connected part of the system and how we react to some of these changes. For example, if we're going back to inspectable properties of remote objects, let's say we have a kind of a widget thing and we have a setter. And when we modify this internal state of the widget, we want to notify whoever might be interested in this change. And we have a notify observer action fired when we detect a modification in such property, let's say a particular field of the object. Very trivial thing. But we're just analyzing the subscription model first. So right off the bat, we have to somehow keep track of these observers. And let's say we want to use a standard vector for this. And we have some sort of loose coupling interface, let's call it iObserver. And we build up such a list of observers of widget. And we're going to see multiple strategies of how to organize that. And first thing that comes to mind is, how do we register? What's the subscription order? In what order do observers sign up for these notifications? And do they respond in the same order as they signed up to receive the DIN notifications. Let's go with a trivial example. Let's say we have the add observer function that receives an opaque observer through some defined contract, this interface, and just pushes back this new observer to the list of known observers for this widget instance. So this would be the most trivial thing that we might be able to do. Almost too simple, right? So what happens if we're trying to add an observer more than once? And might be silly when you think about a toy example like we have on slides, but it's fairly easy when you have a complicated system to end up in such a network of components to end up to oversubscribe, to try to register the same instance twice. And we can guard against that. For example, we can look up this observer to see if we have it or not already registered, and guard against oversubscribing. But the question here is, the solution seems trivial, but the question is more fundamental here. Do we want to allow an observer to subscribe more than once? We might be interested to allow this. Do we expect the observer to be called twice for the same event if it was registered 2 times or 3 times or whatever? Does that make sense? Intuitively, you might say it's redundant. But, and we're going to see more examples later on, there's an important distinction between local reasoning and functional behavior, or the semantic we want to attach to a particular action that we're tracking with an event in the observer system. So on local reasoning scale, we might be interested to register temporarily a particular observer to an event and an actor, whereas in the larger scale of things, that same instance might be registered to the same event for a different purpose in a different location in the code. So there might be scenarios where such a thing of oversubscribing might make sense. So we shouldn't dismiss this as a strategy that should be disallowed or should be considered a bad practice. There might be scenarios where such a thing makes sense, and I'm going to show one such example later. So I mentioned local reasoning. For example, in a function, let's say we're in a function. For this function scope, so while this action happens in our function, just for this scope, we need some kind of observable behavior to be on. And we don't know if in the outer scope we already registered this observer for this particular event. So we want to make sure that we're in contract, where when we execute this action, we need to make sure that everyone who's interested in this event is going to be notified. So we want to have at local to this action, we want to be sure that we have the right connections in the observer network so that the right notifications are received by whomever might be interested. So that's why I'm saying that the same observer might be registered for a different reason in a much wider context or for a longer period of time. But when we're doing local reasoning, we might not know about this, and we want to guarantee that this contract holds. So that's why we might add it and remove it, add and remove this observer at the boundaries of this local operation. And we have no way of knowing at this scope if that was registered or not. Of course, we can be more intelligent here, use an RAII wrapper to make sure that we do the deregistration when we're finished with this operation. We need to make sure that all these operations are properly balanced, adding and removing things and connecting objects properly. Otherwise, we're going to run into other kinds of issues. So, so what can we do to find out if the registration was successful, and more so to find out if this was the first time this observer was registered for a particular actor or action event? So we might change the signature of add observer to return a simple Boolean to know, okay, false means the observer was already registered previously. True means this is the first time we've registered it, a trivial change. So again, we might expect the observer to be called twice for the same event in some situations, and we want to preserve local reasoning or local invariance when doing some localized processing, and make sure that we don't rely on outer scope to set up things for us. It's very similar to how you would think about handling translation units in C++. You want to make sure that your source file includes all its dependencies properly. You don't want to rely on some other thing transitively, including the thing that you might need. And then later on, when somebody changes something, have a brittle thing that just doesn't work anymore. Same kind of reasoning. So unsubscribing, the other side of things. Let's say we want to handle deregistration of an observer. Again, we might look up, okay, let's see, do we have this observer in our list of observers? It was a vector. And if we have it, erase it. But what happens for the multiple registration scenario? What if we remove the wrong instance? For example, if we allowed single registration, if we're removing the observer and it was attempted to be added twice and the second time basically said do nothing because it's already registered, then removing it should be balanced, properly balanced. We shouldn't be removing it if we were not the ones adding it. So we need to keep track of that, and we can. If we allow multiple registration and we enqueue this, let's say we enqueue an observer twice in that vector of observers. Let's say we enqueue it the fifth as the fifth observer in the vector and as the 25th observer in the vector. When we do the deregistration, which one do we remove? Because if we just find if we do this implementation, this naive implementation here, and just say find, we're gonna find the first occurrence and you maybe remove the wrong one. And you might say it's the same reference, it's the same observer. Why should it matter? Well, the order might matter. In an ideal system, the notifications should not be sensitive to the order in which they are sent to different observers. But in reality, you might have such subtle dependencies. For example, you might not realize in a complex system, you might not realize that two notifications or two callbacks as a result of some triggers and such observer notifications might do some actions which happen to work because they're sequenced in a particular way. This happens before that, temporarily. The fifth one and the 25th one in the vector happened in that order. Whereas if one of the things is removed, let's say the first one is removed, and now this observer is notified at the 25th position, this might happen too late after some other actions, some other observers took some actions in their callbacks. And this might be a subtle breakage because we're not aware. So these actions are very order sensitive sometimes. Ideally, they shouldn't be, but sometimes they are. So again, we need to think about what happens with the multiple registration scenario. It's a delicate scenario. And I'm not saying it's wrong to have such a scenario implemented. Again, there might be reasons why an application might need to allow oversubscription. But we need to be aware how to deal with that. We need to be aware how to keep track which instance registered when and when it should be removed. And what happens if the notification comes twice. More examples to follow. We can have a model where removing an observer unsubscribes all instances. That might be something that's acceptable in some scenarios. For example, when you say remove observer, you mean all instances that were registered. Might make sense for a particular application workflow. We can simplify that with C++20. That's just less syntax, nothing different. So who should be notified first? This is how we, let's say we have this strategy of adding observers. And we're doing a lookup, and if we don't find it, we add it. Let's talk about priorities. I've seen situations where people feel the need to organize these observers in some kind of priority buckets, in some kind of rings. Let's say these set of observers, they all need to be notified before the other bucket. So they're, I don't know, more important. They need to take action first. Again, in such systems, you rarely have the ability to control the order of notification. And sometimes there are operations which are sensitive to this order. There's no way around it. And if you rely on such a way of responding to events through these observer rings, then you might have the need to have a special bucket for things that always need to happen before these other things that are less important, or they need to come temporarily after, like happen after in time. So there are situations where you might need to organize things in priority buckets. Okay. The question here arises in how you define the API for registering these observers with priorities. You might be misusing it. For example, there's a chance where, as always, when you add parameters, where you add configurability, you also add more places where you can have mistakes and where bad things can happen. So you might have the observer register with the wrong priority and so on. That can happen, of course. So let's talk about the other side of things now. If we talk about, we talked about registration. Let's talk about notification. Questions so far around registration, deregistration? No, okay, so let's talk about broadcast. We've seen earlier when we saw the widget class, we've seen the setter, and when the value changed, we call this notify observer function, which did a broadcast. This is what it would look like. Let's say it was broadcast the message widget changed, and we'd pass along the reference to this widget that changed. And observers might be interested to examine the properties of this widget and so on. And of course, we can build up more fancier things where you might have specialized broadcast notifications that are tied to particular fields of that object, or are tied to particular changes in that object. So widget change is a placeholder name for all kinds of events that we might want to encode. And we're going to see some examples of such events. But this is the basic mechanic of going through the list of observers in that order. Again, we talked about what order, what side effects this order might have, and just broadcast this event, widget changed. On the other side of things, on the observer side that tunes into this event triggered by the actor, they might implement this function, widget change, and they receive a pointer to the actor, to the sender. This one that we're seeing here, the this pointer. So it will receive the widget that changed. So, and react in some way to the change, like to query some value, query something about the state, do some action, whatever. And the question is it safe to deregister at any time? For example, there might be observers who might be interested in one-time fired event. Like, I'm registering for a particular event in this actor, and I only care about this event once, the first time it happens, after I register, of course. After that, I'm no longer interested. That's a valid scenario. That's a scenario I've seen. And one strategy that you can use is, okay, in my event handler, in my notification, I do respond to the notification somehow, react in some way, take some actions, and then remove myself. You see the call here. I'm calling the method on the actor, and I'm telling the actor to remove me as an observer. I'm no longer interested in this notification. Maybe I'm interested in other notifications, but not this one. So I'm removing myself. Seems perfectly reasonable. I no longer care about this. Remove me from that list. Unsubscribe me from that email list, right? Let's see what happens. So this widget change notification actually was triggered from this for loop, which went through all the observers and called them in order. Widget change, widget change, widget change, each and every one. When we're now in the widget change notification, on the observer side of things, we call remove observer. And we've seen one such implementation of remove observer a couple of slides back. And we did erase from the list of observers. We erased, in this case, all the instances that we've seen there. So we erased this observer from the list. What happens there? Well, we just stepped on our own feet. So we're doing an erase as we're traversing this vector. So we're in trouble. What can we do? How can we make this unsubscribe step to be resilient, to be recursively called? Yeah. How can we make recursive remove more resilient? So one strategy that we can use is to have some sort of sentinel value, some sort of zombie slots, where instead of actually removing an observer from the list of observers right away, we would just mark it as not live anymore in some way. We could use a flag, we could use some kind of sentinel. In this situation, I chose the easiest possible thing that I could do, set a null pointer there, because we have a vector of pointers to I observers. So I just use the null pointer as a sentinel, like this observer is disabled, but I don't remove that from the collection. But then we need the cleanup step. This cleanup step can happen after we're done broadcasting the message. So each time we broadcast a message using the notify observer function, first thing we need to do is check if we have a sentinel or an empty slot there. So that's why I added that if. So if we have an observer in that location, trigger the notification. And after we're done broadcasting the message to everyone, then we erase all the sentinel values, all the zombie slots. Straightforward. Nothing fancy here. It's just a deferred cleanup. Recursive add observer has the same problem, but it's more rare in practice from what I've seen. More problematic is recursive remove, just because of this pattern where some RAI object that does some local guarding or some local adding of the observer or some observer handler just decides to unregister itself. Or more problematically, unregister some other object. I've seen that too. Another consideration is, so far we've seen the actor. So we've seen, it's so way back. let's see. Just to refresh your, yep, this was the one. So we have these M observers, this list of observers that I've been showing around in all these slides. It's a vector inside the widget. So that might be a problem. Let's see why. So it's an intrusive design. Can small objects afford to have observers? Because this vector has a cost. Okay, the observers are not stored inside the object, but we have the vector. The vector has a cost. And for very small objects, when you have lots of them around, you might not afford such an intrusive design. Or from other considerations, from design considerations, you might not prefer the intrusive design. And yeah, even an empty standard vector is not tiny. It has a cost. So when you have lots of these objects, you have millions of these instances, you don't want to carry around always this payload inside the objects themselves. Even, especially if you have instances which have no observers registered, like you're paying the cost without ever needing it. Like you might have millions of instances that might not have any observers registered, and just a couple of them, let's say 5% of those instances might have some observers registered. And you don't want to pay the cost if you're not using that facility. What can you do? You can use tricks like having a lazy vector, let's say, that might have like a first usage, like on first demand, create the vector. You fold in the vector creation when it's first needed. So you play around with the operators there on the slide, and the first time somebody is trying to enqueue to register an observer in that instance, then you allocate the vector for it and register the instance. So you can use a trick like this to have a lazy fold-in creation of the observer list. Another strategy that we can use is, when you have like lots of these small objects, is use an aside data structure. A side place where we record all of these observers and their mappings. Like record, I have here an unordered map from each actor to its list of observers. This has the advantage of not being an intrusive design, doesn't mess around with the semantics and maybe the value semantics of these objects if we want to preserve some meaning to their whole parts of the objects themselves and don't appreciate the intrusive design, or for size reasons, like I mentioned earlier. So this is a valid thing to have an aside bookkeeping for these observers. Problem here is that this aside structure becomes a bottleneck now, because everything has to go through this structure. All the registration actions have to happen through this structure. All the broadcast traversals of the map or this associative data structure, everything has to go through this global registry of all the observers in the system. And that's why I named this global bottleneck, because this can become a bottleneck in the application. But for some scenarios, it's perfectly all right. The throughput needed is not that big, and the application can afford to have this global registry. When you want to optimize for a large network of such objects and don't want an intrusive design. So that might be a perfectly acceptable strategy. Again, I'm reiterating the startup position I had, where I'm saying there's not a unique perfect solution. I'm reviewing some options, and we need to carefully examine what fits in each scenario and in each project. So far, everything I've discussed was a local or a normal sequencing of events. Some registrations happened, some events happened, they're fired, some functions are called. Everything was in some sequence, which we might know or not know, but at least everything happened in some coherent way in the same thread. And I didn't mention threads so far. And this is where the trouble happens, because applications have threads. So like I like to call them multi-lane highway to crashes or congestions, depends on how you protect or what you optimize for. Applications might have threads, and we might have registration events that happen from other threads. We might have, most probably, we might have events that fire from other threads and notifications. And observers which might be called with a particular callback, like widget changed or whatever, might be called with that particular callback, but not on the thread that they expect to be called on. And this can cause serious problems. And even be called from two different threads with the same notification. One event would come, let's say, from on the UI thread, and the same event, same callback for the same observer might come from a totally different thread. Just because of the nature of how the operations happened and where they happened. And sometimes that's perfectly all right. Nothing bad would happen. Things will just work. Depends on what you do in that callback. It depends on what kinds of data structures are you touching, what kinds of functions are you calling. Might perfectly work. Sometimes bad things will happen, probably. And you might have legitimate reasons to switch contexts. For example, you might want to force some kind of affinity for a particular event, for a particular action, a particular message. For example, you might say, this wake up event, this thing, callback I registered for, I receive it, but I always want to handle it on this particular thread. Most common scenario I've seen for this is, I always want to handle this on the UI thread. No matter where this notification came from, I want to handle it on the UI thread. Or you might have some other affinity where you want to handle it for good reasons. And then a valid strategy is to have a way of switching context. And then you need to be able to have a means of executing the action you're called on a particular thread, and have a means of switching executors, switching the context where you run that code that you include. Might be a Lambda, might be your function that you register and so on, but you want to switch the context. That's perfectly reasonable, and I've seen this scenario many times. But again, you need to be aware of such situations. I've never seen situations where you can always query to see, for example, you're being waken up, you receive a notification, and you might query to see, okay, which thread am I on? Am I on the right thread? Have I been woken up on or notified on the right thread? And if not, let's switch to the thing where I want to run this. Rarely I've seen a design where the notification has this information attached. Usually you can query from any location. So what happens if you don't want to switch to a particular context and you want to handle it in whatever context you received it? So from whichever thread you got it from. As always, you can guard with the mutex if you know what data structure you're sharing, what thing you want to modify, depending on what kind of code you have in that handler. You can guard each function with a mutex. Let's say the setter, the add observer, the remove observer, the notify observer, everything that we've seen so far, they might touch data structures which are shared, not obviously shared, but might be shared. For example, the list of observers, the act of adding and removing the registration process, that might be a race condition, because you might have different threads wanting to register for a particular actor at the same time. So they would corrupt that data member, the list of observers, that vector. So the immediate response there is, okay, put a mutex on it. Well, that might fix the problems, not necessarily, but for sure it will tank your performance if that matters at all for you. So it will probably solve the crashes or mask them, but for sure it will not be the best design. It might be affordable for certain kinds of workloads, but it's certainly not the best design, overlocking everything. And what happens if you have this recursive thing that I mentioned early on, where you might be called recursively, let's say the deregistration scenario, where I said, okay, in the event handler, somebody wants to deregister themselves after receiving a notification, and you have this recursive inversion of control there. And what can you do then? Because in that situation, mutex will not do what you want. Recursive mutex, because it's right there in the name, right? Sad news is that I think most of the time where we think recursive mutex might be the solution, it's not. It comes with its own set of problems. Let's say we, in our setter there, back in the widget class, we use a recursive mutex and we lock it with lockguard. Well, it's not bulletproof. For sure, you're not gonna get crashes anymore, but you can get deadlock situations. And this is one of the frequent problems when people think recursive mutex is a solution. More often than not, it's a deadlock recipe. And you might not see it immediately because it really depends on how things interact in the system before you actually see the deadlock happening. So unfortunately, recursive mutex is not the solution. Might work, but it's not the solution. What happens to values? I mentioned values at the very beginning. I said that C++, modern C++ leans heavier on values. And so far we've been talking about pointers and references all over the place and building such networks of objects. So value-oriented design in an object-oriented system. This is directly, that phrase is directly lifted from this presentation, which is excellent, by the way. I highly recommend it, from Juan Pedro Bolivar. The link is in the slides. It's a great presentation on using values in object-oriented system, in classical object-oriented systems, and how you can transition from, let's say, classical C++ with Java influence and early 2000s design of using references and OOP everywhere, and try to move the dial back a little towards values and value semantics, and how you can reconcile these two worlds. And this might come into play and might be handy when we're talking about threads, because usually when dealing with threads, a safer approach, rather than putting locks everywhere and guarding everything, a simpler, more affordable solution would be to make copies. You cannot always do that, but when you can, I highly recommend that you do that. So lean on taking copies if you can, rather than locking. And how can we fit that to our previous code? So in our notify observers, instead of working directly on the list of observers that we have stored there, we're in the intrusive design of the actor, where the list is stored in the widget. So instead of working directly on the list of observers, let's say we make a copy of this vector. And we need to take a lock while copying the vector, but not for longer. So we only take the lock while we touch the list observer, while we're copying it, not for the duration of the broadcast notification. This is an essential distinction. So we don't want to hold the lock for longer than needed. That's a general good practice. So, and in particular here is that we're taking the lock while we copy this vector, which we're copying just pointers there. And we're not taking it for the broadcast operation, not because of performance reasons. You might say, okay, not taking the lock for longer because it's better, it's quicker, or whatever. No, it's because of fear of deadlocks. The difference here is that when we call widget changed, we're calling unknown code. So always when you call unknown code, if you're holding a lock, you might holding a deadlock. So it's when you're you should always be skeptical of calling code that you don't immediately see. And in case of observers, that's by design. Like this is why we build the object system and the observer systems, because you want this loose coupling, and you have an opaque interface. You know you have some observers somewhere, and they might react. You don't know where they are. You know who's observing you. So you're calling unknown code. You don't know what they're doing in their handler functions. So they might want to touch the same structures that you're holding onto. So if you're holding a lock while calling unknown code, most certainly bad things will happen at some point. You might not see it immediately, but at some point you're going to see it. So that's why I'm trying to hold the lock for less time. And again, I'm taking the lock when I want to do the deferred cleanup that I've shown earlier, where again, I'm holding it just while I raise the vector. I'm not calling any external code. I'm not calling any broadcast functions. And the broadcast happens as before. The only difference is that I'm calling widget changed using the copy. You see there, the copy of my vector, to avoid the issues with iterator invalidation and reentrancy issues into this function. So avoid that I corrupt my vector if I have reentrancy into that removal function, like I've shown in the previous slides. So that's why I'm doing it this way. I put the headache emoji there because it's not pretty. Any folks in the room familiar with Qt? Have been doing Qt? A few hands. Okay, better than I expected. So you probably know delete later function. It was a popular idiom many years ago. And in general, even if you're not using Qt, this idea of deferred deletion, of deferred reclamation, I've shown a flavor, a very trivial flavor of it. Even if you're not a Qt user, I think it's instructive to learn about this and look at the idioms, look at how it's handled. I think it's instructive. So if you want to do that. Another presentation that I very much enjoyed is this one by Tony Van Eerd, a few years back now. Thread safe observer pattern. We're doing it wrong. So this is an 1.5-hour presentation where Tony goes through a lot of examples, building from one to another. So basically it's a live demo. The whole presentation is a live demo. Example after example, and trying various strategies. Nothing works. So an hour and a half of experimentation where nothing works. So each time Tony offers a solution, then offers a counterexample or a situation where it fails horribly wrong. So an hour and a half of smart attempts. So don't get me wrong, it's not like he's playing, like deliberately trying to screw up. There's valiant attempts. Some of them I mentioned earlier, a few of them. But much more content in this presentation, so the link is there if you want to follow it. I think it's instructive. And scary, by the way. So a very experienced programmer legitimately trying to build something robust and miserably failing. So I think that's the takeaway here. And again, going back to my initial slide with the one and only solution, I'm not trying to scare people away from using observers, or the way you choose to use it might be totally fine as long as you're deliberate about it, you're aware of the workflows, the constraints you want to keep, the way your system works. You might be on a happy path, and that's totally fine. But if you want to be Machiavelli, there are always going to be situations where you're going to say, okay, this will fail horribly wrong. So that's the talk. That's the Machiavelli talk. Very instructive. So going back to threads. So in a multi-threaded context, it's almost impossible to implement a solid observer pattern. Let's get that honestly on the table. And when I say implement a solid observer pattern, I mean it works in every possible scenario that you might have in the future in application. It might work perfectly for what you're using it and your workflows. And in general, a good takeaway is that in real code, you cannot see the deadlocks until they happen, yeah? And the rule of thumb I mentioned earlier already, don't hold a lock when calling unknown code. So that's always a bad sign. That's why I'm saying if you can, lean on values, lean on copying things instead of sprinkling locks and mutexes all around. Okay, the intrusive design. So in general, we don't want, I started with the intrusive design because it's easier to ramp up and show something. But in general, you don't want to see those things in your objects. Your objects have a different meaning. You want to see the salient parts of the object, the fields that you care about. No, you want to see, don't see this boilerplate, this registration business and this mechanical thing in your objects, in your widget. And one way, and you have, of course, you have multiple events. You don't have just one event like I used so far. You have multiple events. So in one way you can do this is have an actor facade, an actor base class where you wrap up all this business. That's a strategy. Excuse me. And one advantage of doing this is that you have a reusable thing. You can use this actor thing in all your widgets. And it's a generic thing. It's not something specific to this widget. It can have generic events. And in our previous example, it would look somewhat the same way, only that all the boilerplate is moved somewhere under the carpet. It's still an intrusive design, mind you. This being a base class, this is still an intrusive design. But at least the ugly bits are not in your face. And what do I have here? The other side of things where you have the observer, which must implement the interface. That's the contract, the loose coupling we have between actors and observers. That's that thin interface with the events. And the observer needs to add, register, deregister, and of course, implement the events defined in that contract. The interface, the iObserver interface is a contract that establishes that loose coupling, that low coupling between these components. And usually have more than one event. they tend to pile up, funny thing. That's how software works, right? And you have to remember to cancel. So that's why you need to use some kind of RAI wrapper to encapsulate this business of registration and deregistration the way you want it to happen, whichever policy you want to use, the multiple, single registration, whatever. All the business that we discussed previously. So let's say we have a contract like this, where I staff observer, you know I'm good with naming, right? And I have this I staff observer, and I kind of hoped Kevlin would be here because I deliberately put I before all my interfaces, just to annoy him. So he's not here, but I'm still gonna tell him. So let's say I have some events, stuff added, stuff removed, stuff will change, stuff changed, going to sleep, waking up, something, right? This is my contract. This is my interface between my actors and their observers. Problem is you end up having lots of these things. And some programming languages have facilities like optional protocol methods. Interfaces or protocols, these are similar names for same thing in different languages or frameworks. So some programming languages have, like, if you're familiar with Swift, for example, you have optional protocol methods. In C++, we don't have such things, but we can fake it. Like many things in C++, we can fake it, but it's uglier. We can have an implementation which stubs out all these things. And the reason why you might want to do this, if you have a wide contract, contract between your observers and your actors, ideally you should have specialized contracts. But if you have such a wide contract, because life happened, you can ease the burden on the observers. For example, here I have a spectator, which is a staff observer, but instead of implementing the interface directly, it uses this stub, these empty implementations. The reason being, this spectator is only interested in one event out of all that wide contract, just the going to sleep event. This spectator is not interested in other events. So that's why you can use a trick like a stub implementation to avoid boilerplate, like having functions that do nothing in this spectator. Classic thing. What else? So spectator is a staff observer, register, deregisters, and of course implements going to sleep. And it receives this going to sleep event from a particular actor. What happens if my spectator is interested in two actors, two different types? Yeah, not two instances, two different types. And I named them actor and thespian, just because I have a thesaurus. Now I have this event coming from two types, but I have a problem because my function is called going to sleep. And I cannot have two functions here with the same name, right? I want to distinguish between these. I want to do something when actor changes, and I might do something else when thespian changes. Or I want to do the same thing, I don't know. But I have a problem. I cannot have both functions here because in the interface, these functions are defined having a stuff reference, a const stuff reference. Yeah, which might be whatever. What event param I'm interested in. So, as always in software, there's no problem that cannot be solved with another level of indirection. Q Phil Nash, who's not in the room. We can do a trick. We can have a non-typed template parameter here, observer index, and have this int to type business. By the way, does anyone recognize int to type? This is int to type. Anyone? Only young folks in the room? So I was going to say that if you recognize this pattern, you've been writing C++ for a long time. This is actually from the Loki library by Andrei Alexandrescu. It's a long way ago. this into type is just a way of faking a tag dispatch mechanism. So a way of having a type to allow for function overloading. It's just a mechanical trick. And it's nothing fancier than what you see. So all the code is on the screen. That's just a struct with an enumeration there. To have a way of generating types on the fly. So we generate types from those indexes. So we have a type generated from 1, a type generated from 2, literally. From numbers, we generate types. So that we're able to disambiguate between these overload sets. So now we're building overload sets of things. Functions with the same name, but slightly different arguments. And that first argument is just a tag to allow for identifying which actor am I reacting to. And we're going to see how we do that. So how we do that is that we need a proxy. That's the level of indirection I mentioned earlier. That's the periscope kid, the kid with the periscope. So we need a proxy object. And the proxy object will be the one implementing the observing interface, which is iStuffObserver, the raw interface we've seen earlier. And we have this index to make sure we distinguish between them. The number has no meaning, and the order is not important. The single purpose of that index is to generate different instances. And we usually give them usings. We usually give them type aliases to have proper names, better names, not 1, 2, 3. So, and we have the same business as before, only that this proxy object also needs to hold a reference. Where's my pointer? Okay, here's my pointer. So this proxy object that we're building needs to hold a reference to the original observer, the one that's going to receive in the end the notification. So that be the spectator. So it needs to hold the reference to that thing. And this is the implementation. The functions, these are, you can see by the override keyword here, that these are functions from our interface, from our contract. And we have stuff added and stuff removed. I chose just 2 functions. And what we're doing is we're delegating this thing. So we're using our reference to the actual observer, and we're delegating this operation. So we're calling the stuff added, but we're calling the stuff added overload with the right type ID, where the type ID is the thing that we're associating here. The type ID is where we're associating that chosen index. Don't worry, it's ugly, but you're going to see the example on the next slide. It will make sense. So all these events are just delegating to the actual observer, but they're doing so by choosing from an overload set based on type tagging. That's a classic technique. I'm not claiming I invented anything here. So let's see a concrete example. So we have the actor, and the actor is a stuff observer, where stuff observer is this. So remind you, this is stuff observer, and you see it has a non-type template argument. That's just a number. And then I chose 0. It doesn't matter. The number is not important, as long as you're not reusing it. So the actor is a stuff observer, and the actor has an associated proxy type, which the proxy type is this one that we've just seen, the ugly one, the one that delegates. It's in the name, proxy, just does nothing, just delegates to the overload the proper function from the overload set based on the type tag. Type tag is that thing into type. That's the type tag. So that's the thing here. The type tag. This is the type tag. It's a parameter that's not used. It has no value that we care about. It's just so that we choose from the overload set. Wrong direction, sorry. And the thespian is the same. It's a stuff observer. Now we're using the index 1 to make up another type tag. and it has its own proxy. So each actor has to have its own proxy. Sounds ugly. It gets better. Now, how we're using it. So now we have an observer that is interested in, let's say, a particular notification, let's say, wake up or whatever, some event happened, from two types of actors, from two types of senders, from the actor type and the thespian type. And what we need to do is use these proxy actor and proxy thespian, and we're using them as bases here. So these are the proxies. You see them? And this is where we're using it. And we need to hold on to these proxies, which have zero cost. These proxies inside have one reference. So they do nothing. So they have one reference. So each of these is one reference to the, inside has one reference to the original observer, which the original observer is this. And this is why we initialize them as such. So actor proxy, which is this member, is initialized passing star this, and star this goes here. It goes here. So that's why I said this is the original observer, the intended receiver of the message, right? So we associate each proxy with this spectator, so the actor proxy with this spectator and the thespian proxy with this spectator. And when we register the observers with the senders, with the actor and thespian, so with the actual things that we're trying to observe, instead of registering ourselves, so before we did .add observer star this and .add observer star this, now instead of registering ourselves, we register our proxies, whichever proxies we might have. So that's what we're doing. We're registering our proxies instead of directly. And when the notification happens, this function, which is a unique function, you see this one doesn't have a type tag. Because we registered our proxy, when this proxy is called with the stuff added event, it will just find the right stuff added in my spectator class. Same thing when stuff removed this event happens. So now, in my spectator, I can have multiple functions. This is why I said an overload set. Let's say I have the going to sleep event. So I can have as many going to sleep events. Let's say in this situation, I'm interested in stuff added just from the actor. So I'm interested in this event just from the actor type. And that's why I'm using this type tag that I defined earlier with the using declaration. So I'm interested just in the stuff added event from the actor type, but I'm interested in the going to sleep event from both types. I care when the actor sleeps and the thespian sleep. So I can now disambiguate between these events based on their types, right? Any questions? I know it was a lot of code, but I tried to split it in slides. Do I need to go back to a particular slide? It's all right to say I'm confused. I was too. Good? Okay. And these are the using declarations, just some boilerplate, which I neatly wrapped up in a namespace. So it all looks ugly and seemingly unnecessary. The advantage is that these are reusable components. So these observer proxies, so the actor, the thespian, and the spectator, those are concrete types. Those are specialized on whatever they're doing. The actor, the thespian, and the spectator. Those are the moving bits. But this dance, this boilerplate, this dance here with the proxy, the ugly bits that I showed earlier, these are reusable components. That's why they're templates. So I can, whoops, sorry. So staff observer proxies can be reused for any other types. And that's why we did the ugly thing once, and we're using it. And they're only tied to that contract. So if you have another interface, another type of contract, you naturally have other types of such proxies, because they encode the operations. You saw that the proxies, the proxy has the stuff added, stuff removed, going to sleep, has these parts of the contract because they implement this interface, iStuff Observer. So they're specific to a type of contract, but they're not specific to the types of objects involved in that contract. So as long as I have, let's say, a network communication protocol, which is my interface, as long as that contract is established and it has a set of functionality, a set of functions defined with a set of vocabulary types that we agreed upon as communication, then I don't care about the types of components that use that communication protocol. What types they are. They might be sockets, they might be piped memory, they might be, I don't know, emulators, interfaces, mocked objects in a test framework. So we don't care about the particular types involved. We care only about the type of contract in place. So that's why I say they're usable for a particular contract. Going back to all the mess with the notifications, when I mentioned threads and everything, observer networks form global state. They usually tend to be big networks. They tend to be involved things. So once you have such a system in place, it tends to grow. And these networks kind of form global state. It's the same reason I dislike shared pointer. So building such shared pointer relationships always builds a huge network of global state in your system. So they have advantages. They have many advantages of low coupling, of doing these remote notifications, this spooky action at a distance that sometimes might be surprising. They have many appealing qualities. They come with many disadvantages. It's a compromise, but it's a global state. And as all networks that form a global state in your system, they tend to have the same kinds of problems. Problems related to memory management issues. You might have dead subjects, missing observers, and all kinds of things that might be mishaps in how you might not do proper registration, deregistration in the system. And if you're not doing a proper bookkeeping of the system, it's not a specific problem to observers. It's a general problem. So as it tends to have the same problems that global networks of objects in a system have. So blissfully dangling might be a thing that happens. So be aware of this. We need to deal with such situations and understand the interactions in a big network of objects. And with that, I'm ready for questions or comments. Question was for the audience. Question was, do I have a library for these facilities, or do projects usually build something based on the particular needs? Because I mentioned reusability of certain parts. The answer is, I think it's very hard to have something that's general purpose. It's very hard to have something that works for everyone, for some of the reasons I explained earlier. So I think it's for such complex systems. These are complex systems with complex interactions. I think you need to understand what your actors are, what kinds of operations happen in your system, what's the data flow. This is one of prime examples where analyzing and understanding data flow through your system is very important, and how you transform data. So I think it's best if you avoid finding mythical general solutions. Like, understand your system, build the minimum required thing, don't over-engineering it, don't try to over-engineer it, build a minimum thing that fits your constraints, document your constraints, put checks in place to make sure that you don't break those assumptions, because the system might be simple at the beginning and people might deviate, or requirements might deviate, as always. So try to have checks in place to make sure you're always in contract, you always do the assumed thing, and build something that's appropriate for your workload, rather than try to find a magical answer for everyone. It's not easy. And I wouldn't even try, honestly. So everything I've shown are bits and pieces from different scenarios that I found useful. They don't even all fit together in the same thing, although I made them fit in the slide. Repeat the question. So I've shown only examples with interfaces and and some overrides and virtual functions, and how would that work with using standard function, for example? So that was the question. So because standard function has ownership semantics and can carry a deferred operation, might work. So for example, you might imagine a system where you register, instead of registering an observer, you register a block to be executed. Like you say, execute this block, and by block I mean a lambda, or you can wrap it in a standard function if you want. But at least at the API level, you have to wrap it in a standard function to hold on to that piece of code. But you might imagine a design where you say, when this event happens, execute this block. And then the system takes that block and holds on to it in a standard function, because it can, it must outlive that invocation to be executed when that event fires. It comes with the same set of problems. For example, that function might capture things that might not be around when you defer execute it. So you need to, like I said, you need to copy things if possible, not rely on things sticking around. Or if you're accessing things which are some other parts, like a reference or a pointer, so any kind of indirection there, then you need to make sure it has the same problems. You need to make sure that it's still around when that standard function is invoked. But at the design level, at the API level for registering for such events, I don't see a problem using something like enqueuing a lambda or and capturing something through a standard function for deferred execution when that event happens. So I haven't tried it, but I think it's feasible.
The proxy object seems very similar to kind of what that function does.
In some way, yes. Yeah. I could imagine such a system. And I think I've seen similar things in AppKit and UIKit a few years back, when I played around with developing iPhone applications and Mac applications. And I remember there were some APIs where you would register an Objective-C block, nowadays Swift block, to be executed when some event in UIKit happened. So it was a very similar thing. It was a different mechanism to achieve the same thing that, for example, in Qt was achieved with signal slot mechanism and associating callbacks. But in Objective-C and Swift, I remember there were some APIs where you gave it a block of code, and it used to execute that block when some event in the system fired. Like, for example, when the user scrolled the list view or tapped or something, it called your code later when that event fired. So it's the same kind of thing where you register to an event. In that case, it was a UI event. And it executed some code that it captured from you. It came with the same set of problems. Like, you need to make sure that you you capture the thing on a heap, the context. The blocks were I remember at the time they were using Arc, and you had to be careful for that block to be copied on the heap to still be around.